Okay, here we go. Let's see, we have learned 5 tests so far. We're going to learn 2 today, so we will have 7 under our belt. Today we're going to look at the direct comparison test and the limit comparison test. Alright. Okay, so I think the letters here that they use for the nth term, are a little confusing because here and here they change, but we're meaning the same thing. So let me specify. We're changing back and forth from the A sub n to B sub n because we're really talking about 2 different series. One which we are given and one which we get to choose. Alright, that's what we are looking at. So this row, if you will, or column, these are ones that we choose. Okay, these are the ones that we're going to choose. These are the ones that we're given. Because we need to really distinguish that. This is like your problem. This is what you're given. This is the problem that you are trying to solve. And these are the ones these are the different series that you're going to choose to use in this test. So that's the first thing I want to clarify, is that the letters are changing because their place in the inequality is changing. They're trying to keep the inequality statement the same. So instead of changing the inequality statement, they're changing the name of the series. Okay, so let's talk about each one. So if I choose a series that converges, and I compare it to the one that I have, so here's the one that I have, I would basically, the one that converges would need to be larger than the one that I have for this test to work. This is the one that I have. Okay, so I choose a series that converges. I compare it to the series that I currently have. If the series that I choose is larger than the one, the series that I choose is larger than the one that I had, then the test works, and it proves that my series converges, the one that I had. So, if this is for converges. And a lot of times there's a little saying that goes with this, and that helps some students. The little sayings help some students, so I'll write it up here for you. Less than a convergent series converges. Less than a convergent series converges. And we're going to do examples of these. Hopefully that will clarify some of the things that I'm saying. You're probably thinking, what is she talking about? That's okay. We're going to work through some examples. So let's look at the other choice. Let's say that I choose, here's the ones that I'm choosing over here. Let's say I choose a series that diverges. And I'm going to compare it to the series that I have. This is the series that I have. If I choose a series that diverges, then the series that I have needs to be larger than the one that I chose. This series that I have needs to be larger than the one that I chose. Okay, and then the one that I chose will diverge. And the little saying that goes with that is greater than a divergent series diverges. Greater than a divergent series diverges. So the goal with this test is to find a series that's comparable that you know stuff about, compare them, see which one is larger, and then this gives us our results. Now, there will be times when we can't use this test. There will be times when we choose a convergent series and it's actually smaller than the one that we picked. We can't use the test in that case. Okay, so there will be cases where the test doesn't work. If the test doesn't work, you pretty much have to throw out the test and try something different. Okay. So, let's practice. Now the choosing what to compare to sometimes is a challenge. Well, basically, let's just take a look at this one. What we can do, if this, let's say this had n cubed plus n squared plus n and over, 1, something like that. Typically, which is actually kind of nice, typically these other terms can usually be discounted. And this series, 1 over n cubed, will behave similarly to the series that we have here, the plus 1. What we're basically doing is narrowing it down to a small series that we know how to work with. In this case, this is going to be a p series with a p of 3. So, and we'll go through and we'll pick what to choose. We'll choose all along here, and hopefully you'll get kind of the hang of it. And so generally it does work out to where if we choose the largest in the numerator and the denominator, I'm talking about exponent wise, we can discount the rest of it. That usually works out that way. So what we're going to do is we're going to compare to this series, 1 over n cubed. And this has a p of 3. And when it has a p of 3, is this convergent or divergent? It's convergent. This converges by the p series. Okay, so this information is on all the information about what I have chosen, the series that I've chosen to compare with. So then what we do is we set up an inequality, and we always put the original series first. That will just help you. That'll just keep you kind of focused. We always put the original first. And we put the one that we chose beside it. And then we compare them, and we try to determine, or we will determine, which one is larger, and we'll decide which way to put our inequality. I do this, and I suggest that you do this by numerically, like putting a 1 in. If I put a 1 into this, I get 1/2. I put a 1 into this, I get 1. Okay? Right now it looks like that one is larger. So we try it with another number. Try a 2. If I put a 2 in this one, I get, 1/9. I put a 2 in this one, I get 1/8. Still holds true, doesn't it? So our inequality is correct. Let's see if this is going to allow us to make a determination. So what we found is that the series that we chose, which converges, is larger than our series. That's what we're looking for, right? Our series, the convergent series we chose, is bigger than the one that we have. So that falls under this category. Ours is less than a convergent series, so it converges. So we can say, therefore, converges by, and we can just say comparison test instead of direct comparison test. That would be fine, because the other one we're going to call it the limit comparison test, so we can just call this comparison test. So it converges by the comparison test. Now, let's look at the scenario. What if this had gone the other way? What if our original series was larger than the one that we chose? That means that this test would be inconclusive. Now, I had another student ask, well, what if we went back and chose something different, like 1 over n to the 4th? Well, if I compared it with 1 over n to the 4th, is 1 over n to the 4th comparable to 1 over n cubed? Not really. It's not close enough. We're trying to get something close. We're not just doing wild guessing. We're trying to get a series that is close to the one that we have. So we can't change the exponent. Okay? That's this right here. This is a p series with an exponent of 3. That p is 3, and by the p series test it converges. That's a test we learned yesterday or the day before. I can't remember. Yesterday? Okay. Yep. All right. How's our first comparison test? Not too bad, right? This, we put the original series first. ORIG. Original series first in our comparison. That's what we're doing here. And then we put our comparison. No. Okay, so then we could make the case, well, why can't I do n to the 5th? Or why can't I do n to the 1,000,000th? We need to be as close as possible. Okay, we need to be as close as possible to the original so that our, because if we're close to the original and we don't get the results that we want, maybe we aren't going to get the results that we want. You know, we can't change it to a higher power just to get something to work the way we want it to. We have to compare with something close to what we have, as close as possible. Okay? All right, let's take a look at our next one. So what I do, I just kind of circle it. That's what I focus on, is the largest, the top and the bottom. So we're going to choose, we're going to compare to this series. We can rewrite the way this looks, and basically you probably recognized it before I rewrote it. So this is geometric. And by the way, these are the most convenient types to do this test with. If what you're comparing to is like a p-series or geometric, very straightforward. That's really what we're looking for with this test. Something we can tell pretty quickly whether it converges or not. So with this one, this is geometric. This has an R of 1/3. And so by the geometric series test, what does this one do? It converges. So this one converges by geometric series test. Okay? So that's all the information on what we're comparing to. Alright, so let's start our comparison. We write our original one first, so 1/3 to the n plus 2. We write our comparison one next, and we determine which one is larger. So again, I would substitute a 1 in. Let's see, here I would get 1/3. Over here I'd get 1/5. Looks like that one's bigger. I would double check it with another number, maybe 2. I'd get 1/9. Over here I would get, what, 1/11th, and so that still holds true. This, the one that we chose is larger, and this is convergent. So it's the same scenario as the first one that we did. Our series is smaller than the one that we chose, and the one that we chose converges. So therefore, we converge, or this converges, by the comparison test. Okay. The last one on this slide, I'm going to choose, I'm going to compare to this series, 1/n to the 1/2. And that is a p-series, right? Where p is a half. So p is 1/2. And what does this one do? Does this converge or diverge by the p-series? Diverges. This one diverges by the p-series. And again, all this information is on what I have chosen to compare to. Okay, so we list our original first, and our one that we chose second, and then we test to see which one is larger. Alright, so this one starts at 4, so I'm going to start at 4. If I put a 4 in here, we get, what, 1/2. This gives us 1, right? Looks like we're going that way. So let's do one. I mean, I'll probably check with a 9. Let's check with a 9. So square root of 9 is 3, so this side gives me 1/3, and this side gives me 1/2, so that holds true. Looks like we chose correctly. So the one that we chose, which is divergent, is smaller than our original one. Does that match this? It does, doesn't it? Greater than a divergent series diverges. And again, we have to be very close. The series are very close that we're comparing. So this meets our criteria, so therefore we diverge by the comparison test. Okay, and that is on the direct comparison test. Okay? Are you talking about this? Okay, so this one is not this one. Okay, they're different series. What I'm doing is I'm using this series to prove that this series does something, but they're completely different. So what I have to do is prove by this test that this is valid. Okay? What if this were a plus 1? Would this still hold true? Right? No, it's still the plus 1, this one is still going to diverge, but then this scenario is not going to be set up properly because it won't be this way anymore. If this were plus 1, which one's going to be bigger? This one's going to be bigger. And so the test fails. We can't use it. Does it converge or not converge? Why, I don't know. We have to try another test. So we can't just look at it and say, oh, well, that's going to converge, because I promise you the minute that you do that, it's not going to. You have to use a test to prove it. It's like a proof. Like in geometry or trigonometry, when you're trying to prove stuff, you've got to use a test to prove it. You can't just eyeball it and say, this is what it's going to be. Okay? You have to use a test. I have been asked, and actually I've been asked that question several times in different contexts with different tests. Well, I know it's going to do this. Can't I just say it? No, you have to say what test proves it. The grader is not interested in what you know that it does. The grader is interested in knowing that you actually have mathematical proof that it does. Okay, you have to use the test to prove. That's our whole purpose in learning the 10 tests. Okay? All right. So let's look at our next test that we're going to learn today, which is the limit comparison test. All right, so this is a different scenario. And by the way, on the other one, on the direct comparison test, the nth terms, the a sub n and b sub n, hopefully you noticed at the top, they have to be positive. They can't be like alternating series. That won't work. They have to be positive. And the same with the limit comparison test. If you have an alternating series that goes negative, positive, you can't use one of these tests. You have to use a different test. All right. So we have to, again, for this one, it has to be positive. And what we're going to do, how this test works, is that we make a ratio. We make a ratio of the original with the one that we choose. We make a ratio. And we take the limit. If our answer to the limit, which they're calling L, turns out to be finite and positive, then the two series go hand in hand. They either will both converge or both diverge, depending on what the scenario is. Okay, so that's how this test works. It does not matter which one you put on top in the numerator. It doesn't matter. The one that you chose or the original, it makes no difference. The test will still work either way. Okay, so let's try that. So here we're looking at this. What I would do is simplify that. I wouldn't use that. I would actually simplify that. So that looks like that's going to simplify to 1 over n. And I don't use constants. I don't pick constants in my series that I use as my comparison. I just do a straight series. So we're going to compare to this series, which would be 1 over n. So that's a p series. P equals 1. And what does the p series test tell us about that? It diverges. This one diverges by the p series test. Okay, and this is the information on what I'm using to compare to. Alright, so let's set up our ratio. Again, it doesn't matter which one you put in the numerator. I usually put the original one in the numerator, but it doesn't matter. So the limit as n goes to infinity. So our original one is n to the 4th plus 10 over 4n to the 5th minus n cubed plus 7. That's going to be over 1 over n. And so I fix my complex fractions, and I get the limit as n goes to infinity, n to the 4th plus 10 over 4n to the 5th minus n cubed plus 7 multiplied by, that's going to flip up, n over 1. And just to clean it up a bit, again, I'm showing several steps. You don't have to. We have n to the 5th plus 10n over 4n to the 5th minus n cubed plus 7. So I would bet the majority of us are at the place where we can just look at this limit and say what it is without doing anything algebraic. Right? This limit is 1/4. So 1/4 is finite and positive. So this is finite and positive. Therefore, our original series diverges. So what does that mean about our series? It diverges. They go hand in hand. So therefore, it diverges by the limit comparison test. Okay? So we diverge by the limit comparison test. We okay on that one? Okay, last one. I'm going to compare to this series. Notice how I'm starting my series at the same place they are. Starting it at 2, just like they are. This is a p series. P is 3. And what do we know about p series when the p is 3? It converges. So this converges by the p series. Okay, again, this is all the information for the one I'm comparing to. So let's set up our ratio. The limit as n goes to infinity of 1 over n cubed minus 2 over 1 over n cubed. Okay, I'll rewrite that. Okay, what is that limit? That's going to be 1. 1 is finite and positive. Therefore, what is our conclusion? Therefore, yep, it converges by the limit comparison test. All right. So those are our 2 new tests.